Hi, my name is John Ceribes. This is my Lab 3 report for Physics 1, Black Hole and Orbits. This is the title. I built two models, one to weigh a black hole, and then one to fly a spaceship around a planet and its moon. There are two parts in Model 1. A star of known mass orbits a black hole of unknown mass. The star is my system, the black hole is my surroundings, and I work backward from its motion to the black hole's mass. In Model 2, the spaceship is a system, and I find its initial velocity that loops it around both the planet and its moon without crashing. Four ideas that are used in these labs. Newton's second law, which means net force equals the rate of change of momentum. The law of gravitation, which is g times both masses over distance squared. The velocity and position update formulas, which step the measure forward. And the fact that the component of derivative p over derivative t parallel to motion changes the speed, where the perpendicular part changes direction. Here's a quick preview. In part 1, the black hole came out to about 1.2 times 10 to the 34th kilograms, around 5,600 solar masses. In part 2, a ship velocity of negative 400 gave a stable orbit that ran the full 700 hours. Part 1, nope, move on to the next one, yeah. Part 1, my system is a star. Mass 2 times 10 to the 30th is the mass. The surroundings are the black hole. And it's fixed to the origin, and its mass is unknown. The key assumption: gravity from the black hole is the only force on the star. My inputs are the speed from my EM of the star, and delta t equals 86,400, 1 Earth day. In the loop, I find the star's momentum before and after each step. The change of momentum over time gives the derivative over p over t, which by Newton's second law is the net force. This net force is gravity. I rearrange to solve for the black hole's mass every point, then average them all together to get an answer. Here's a result. You can see it on the right. Every loop, or yeah, that's the result. So what does it mean? Net force and rate of change are equal by Newton's second law, but they mean different things, and that's what I measure. Straight from the star's motion, no mass is needed. Net force is the cause, the gravitational pull, but computing it needs the mass is what I'm looking for. So setting the measured dp over dt equal to the pull is what lets me solve for the mass, and the components match. So parallels change of speed, perpendicular change of direction. And the spaceship is my system, starting on a hill on the moon. The surroundings are the planet, the origin, and the moon circling it. Masses are all given. I picked a ship, velocity of negative 400, 0, below light speed, so it's allowed. Found by testing values on the loop sides of the body. Each step I compute 4 gravity forces: planet on moon, ship on moon, planet on ship, moon on ship. I sum them to net force and then average them. Then I apply Newton's second law and the position update to move both. The minus sign makes each force attractive. Here's the orbit. Magenta is a ship's loop that circles the planet, no crash, and yeah. What if I modeled the whole system? Black hole, star, planet. I need every pairwise gravity force. Nothing would stay fixed, but that wouldn't matter equally. There's a mass hierarchy, which means the black hole dominates the star holds the planet holds the moon guides the ship, and then yeah. So, and the tiny ship barely pulls back on anything. So you can include everything, but a few dominant interactions set the behavior. That's what occurs. Looking at sources of error, both models use a finite time step, which drifts over long runs. Part 1 estimates velocity from different positions or from position differences, which is why averaging helps. Both are, and yeah, the averaging is ideal, and the ship's velocity was hand-tuned, so that was a really wide range. And then to wrap up, Newton's second law and gravity did all the work. Here, part 1, weighed the black hole at 1.2 times 10 to the 34th without knowing its mass in advance. Part 2, put the ship on a stable orbit around both bodies, and that worked. So thank you for watching.